Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence and robotics research. Today's episode focuses on recent advances in robotics research, examining breakthrough papers that are pushing the boundaries of what autonomous systems can achieve. We'll be synthesizing findings from multiple research papers to provide you with a comprehensive understanding of where the field stands today and where it's headed tomorrow. From autonomous vehicles to humanoid robots, we'll explore the technologies that are transforming how machines interact with our world. Join us as we dive into the fascinating developments that are shaping the future of robotics. Robotics represents one of the most interdisciplinary fields in modern technology, sitting at the intersection of mechanical engineering, electrical engineering, computer science, and artificial intelligence. What makes this field particularly fascinating is its broad scope, spanning everything from hardware innovations in sensors and actuators to sophisticated software algorithms that enable increasingly complex behaviors. We're witnessing a significant transition as robots move beyond controlled industrial environments into our homes, hospitals, and even disaster zones. This evolution is addressing critical societal challenges, from caring for aging populations to operating in environments too dangerous for humans. Creating effective robotic systems requires expertise across multiple domains, designing physical mechanisms that can interact with the world, developing sophisticated sensor arrays that can perceive the environment, crafting control algorithms that can process this information, and implementing advanced AI techniques that enable adaptive behavior. This interdisciplinary nature creates both challenges and opportunities as researchers work to integrate advances across these different domains. The first major research theme we're exploring today is autonomous vehicle navigation, specifically the critical balance between making progress toward a destination and ensuring safety. Recent work by Abueluzma and colleagues has yielded impressive results, developing risk-aware objectives for reinforcement learning that reduce collision rates by 21% compared to baseline approaches. This represents a significant step forward in addressing one of the key challenges in autonomous driving. Another important advance comes from Baden and colleagues, who enhanced trajectory prediction capabilities by incorporating class-specific models that account for the different behaviors of various road users like pedestrians, cyclists, and other vehicles. This makes predictions more trustworthy and contextually appropriate. Additionally, researchers have developed road-aware boundary-guided frameworks that ensure the physical feasibility of predicted movements, preventing systems from planning impossible or dangerous maneuvers. These advances employ novel hierarchical frameworks that explicitly incorporate safety considerations into reward structures for reinforcement learning systems. Collectively, these innovations are addressing key barriers to the widespread deployment of autonomous vehicles by making navigation systems more robust, safe, and predictable in complex real-world environments. Our second research theme focuses on multi-robot coordination and swarm intelligence, an area that's seen remarkable innovation. Jane and colleagues have created the JaxRobotarium platform, which dramatically accelerates both the training and deployment of multi-robot reinforcement learning policies. This platform achieves training speeds 20 times faster than previous approaches and simulation speeds 150 times faster, while maintaining high fidelity. This represents a transformative tool for researchers in this field. In another groundbreaking approach, Lee and colleagues pioneered the LLM-Flock framework, which leverages large language models for decentralized coordination of robot swarms. By combining the reasoning capabilities of language models with consensus protocols, they've achieved stable flocking behavior that adapts to changing conditions. We're also seeing practical applications emerge, such as Krishnakumar and colleagues' work demonstrating how drone swarms can be used for three-dimensional environmental monitoring, creating detailed reconstructions of phenomena like smoke plumes. These consensus-based protocols, when combined with language models, achieve stable coordination without centralized control. The applications for these technologies range from warehouse automation to search and rescue operations, environmental monitoring, and distributed sensing tasks. This research is expanding the range of tasks that robot systems can accomplish through effective collaboration. The third major research theme explores humanoid robotics and loco manipulation, the challenging integration of locomotion and manipulation capabilities. John and colleagues have developed the Falcon framework, which enables unprecedented force-adaptive manipulation while walking. This system uses dual-agent reinforcement learning to coordinate the many degrees of freedom in humanoid robots, allowing them to perform complex manipulation tasks even while maintaining balance under significant external forces. The Falcon system can handle forces up to 100 newtons during cart-pulling tasks while maintaining stability, a remarkable achievement in humanoid robotics. Complementing this work, Dane and colleagues created the Jaeger controller, which takes a different approach by separating upper and lower body functions. This dual-level control strategy addresses the dimensionality challenges inherent in controlling complex humanoid robots with many joints and degrees of freedom. By decomposing the control problem, they've made it more tractable while maintaining coordination between different body parts. These advances represent significant progress toward robots that can operate effectively in environments designed for humans, combining the ability to move through spaces and manipulate objects simultaneously, a capability essential for real-world applications from home assistance to industrial tasks. Our fourth research theme addresses the critical challenge of bridging the gap between simulation and reality in robotics development. Geezer and colleagues have developed an innovative hybrid digital physical testbed specifically designed for ship autonomy research. This system combines physical model ships with digital simulation components, creating a controlled laboratory environment where algorithms can be validated before deployment on actual vessels. This approach significantly reduces the risks and costs associated with testing autonomous maritime systems. In a different application, Belove and colleagues demonstrated the effectiveness of reverse curriculum learning for teaching robots complex physical tasks. Their work showed how quadrupedal robots could learn to mount skateboards, a challenging task requiring precise coordination, by gradually increasing task complexity rather than attempting the full task immediately. This gradual approach enables robots to acquire skills that would be difficult or dangerous to learn through direct trial and error in the real world. These simulation-to-real transfer techniques are critical for accelerating robotics research and deployment, allowing researchers to develop and refine algorithms in safe, controlled environments before transitioning to real-world applications. This research theme is particularly important for bridging the gap between laboratory prototypes and practical, deployed robotic systems. Examining key findings across these research papers reveals several breakthrough results that represent significant advances in robotics. The Falcon framework developed by Zhang and colleagues enables unprecedented force handling capabilities in humanoid robots, allowing them to perform manipulation tasks while walking and handling forces up to 100 newtons. This represents a major step forward in humanoid robotics, extending their potential applications to tasks requiring significant physical interaction. The JaxRobotarium platform created by Jane and colleagues is democratizing access to multi-robot learning research by dramatically reducing the computational resources and time required. By accelerating training and simulation by orders of magnitude, this platform lowers barriers to entry and accelerates innovation in multi-robot systems. Lee and colleagues demonstrated effective integration of large language models with robotics through their LLM-Flock framework, showing how the reasoning capabilities of language models can enhance robot coordination when properly integrated with consensus mechanisms. Abueluzma and colleagues achieved significant safety improvements in autonomous driving through risk-aware reinforcement learning that reduces collision rates while maintaining performance in terms of route progress. Additionally, Zhu and colleagues showed how vision-language integration can enhance object navigation and environmental understanding, enabling robots to develop more nuanced and flexible understandings of their surroundings. These findings collectively represent the cutting edge of robotics research today. The methodological approaches driving these innovations span several key techniques that are transforming robotics. Reinforcement learning has evolved to include dual-agent architectures that decompose complex control problems into more manageable components, as seen in the Falcon framework for humanoid control. This approach addresses the curse of dimensionality that has historically limited humanoid capabilities. Large language models are being integrated with robotics in novel ways, particularly through consensus protocols for multi-robot coordination. This integration leverages the reasoning capabilities of language models while ensuring stable and consistent behavior across robot teams. Simulation environments have advanced to include hybrid physical-digital test beds that enable safe algorithm validation before deployment on real systems. These environments strike a balance between the control of simulation and the fidelity of physical testing. Curriculum learning approaches are being applied to teach robots difficult physical skills by progressively increasing task complexity. This technique mimics human learning processes and enables robots to master tasks that would be challenging to learn through direct experience. Sensor fusion techniques are employing neural networks for tasks like bias prediction in visual inertial odometry systems, improving the accuracy of state estimation for robot navigation. These methodological innovations collectively represent the toolbox researchers are using to push the boundaries of what's possible in robotics. Let's examine one particularly significant research contribution in detail: the Falcon framework developed by Zhang and colleagues. This represents a breakthrough in force adaptive loco manipulation for humanoid robots, addressing one of the fundamental challenges in the field. Traditional approaches to humanoid control have struggled with force adaptation, limiting robots to lightweight tasks or requiring wheeled platforms for stability. The Falcon system overcomes these limitations through an innovative dual-agent reinforcement learning approach that decomposes whole body control into specialized lower body and upper body agents. This decomposition addresses the curse of dimensionality that has historically made humanoid robot control so challenging. The system can handle forces up to 100 newtons for cart-pulling tasks, 40 newtons for door opening, and 20 newtons for transporting payloads, all while maintaining balance and precise control. This represents a significant advance over previous systems and opens up new possibilities for humanoid robots in practical applications. The framework achieves this capability through its dual-agent architecture, which allows for stable locomotion under force disturbances while maintaining precise end effector tracking. This research was selected for detailed examination because of its potential to transform humanoid capabilities in real-world applications, from industrial settings to disaster response scenarios where significant physical interaction with the environment is required. Another groundbreaking contribution worth examining is the JaxRobotarium platform developed by Jane and colleagues. This platform for accelerated multi-robot reinforcement learning achieves remarkable performance improvements: 20 times faster training and 150 times faster simulation compared to baseline approaches, while maintaining high simulation fidelity. What makes this platform particularly significant is how it dramatically lowers the barrier to entry for multi-robot research. Tasks that previously required hours or days of computation can now be completed in minutes, enabling more rapid iteration and experimentation. The platform includes standardized coordination scenarios, including novel ones that adapt established multi-agent reinforcement learning benchmark tasks to realistic robotics settings. This standardization enables more meaningful comparisons between different approaches to multi-robot coordination. The acceleration is achieved through effective parallelization and hardware acceleration using JAX, a high-performance numerical computing library. By providing these standardized scenarios and computational efficiency, the platform enables researchers to focus on algorithm development rather than infrastructure concerns. This research was selected for detailed examination because of its transformative impact on research accessibility and iteration speed, potentially accelerating the pace of innovation in multi-robot systems for applications ranging from warehouse automation to search and rescue operations. The LLM-Flock framework developed by Lee and colleagues represents another innovative contribution worthy of detailed examination. This novel framework applies large language models to decentralized robot coordination, specifically addressing the challenge of stable flocking behavior. While previous attempts to use language models for robot formation control often resulted in unstable behaviors, LLM-Flock overcomes these limitations by integrating language models with an influence-based plan consensus protocol. The researchers evaluated their approach with various state-of-the-art language models, including both closed-source models like Claude 3.5 and open-source models like Llama 3.1-405b, showing consistent improvements in stability, convergence, and adaptability. What makes this result particularly significant is its demonstration that the reasoning capabilities of language models can be effectively harnessed for robot coordination when combined with appropriate consensus mechanisms. This suggests a new paradigm for robot coordination where the sophisticated reasoning capabilities of language models can be leveraged for complex decision-making, while specialized algorithms handle the consensus and coordination aspects. This hybrid approach could enable more adaptive and intelligent multi-robot systems capable of operating in dynamic and uncertain environments. This research was selected for its pioneering integration of language models with robotics, potentially opening new avenues for more flexible and adaptive robot coordination systems. Looking toward the future of robotics research, several emerging opportunities and challenges are shaping the field's trajectory. One significant direction is the integration of foundation models with robotics to create more adaptive autonomous systems. As large language and vision models continue to advance, their incorporation into robotics frameworks promises to enhance robots' ability to understand and respond to complex, unstructured environments. Another important frontier involves scaling humanoid capabilities for real-world deployment in human environments. The advances in loco manipulation we've discussed represent important steps in this direction, but significant challenges remain in making humanoid robots robust, safe, and cost-effective enough for widespread deployment. The development of standardized benchmarks and platforms for reproducible multi-robot research represents another crucial direction. As we've seen with the JaxRobotarium platform, such standardization can accelerate innovation and enable more meaningful comparison between different approaches. Bridging the gap between simulation and reality remains a persistent challenge, with researchers working to develop faster deployment cycles through improved transfer learning techniques and hybrid testing environments. Finally, as robots become more capable and autonomous, addressing ethical and safety considerations for their integration into society becomes increasingly important. This includes not just technical safety mechanisms but also considerations of privacy, autonomy, and the societal impacts of widespread robot deployment. This synthesis of recent advances in robotics research was created using several AI tools working in concert. The primary content analysis and synthesis was performed using Anthropic's Claude 3-7 Sonnet model, which analyzed research papers and extracted key themes and findings. Text-to-speech synthesis for this podcast was performed using Google's TTS technology, creating the natural-sounding narration you're hearing. The visual elements accompanying this podcast were generated using OpenAI's image generation capabilities, creating conceptual illustrations of the robotic systems discussed. While AI tools were instrumental in creating this synthesis, all content underwent review by human experts for accuracy and coherence, ensuring that the technical details and research findings are presented correctly. This combined approach leverages the strengths of both AI systems and human expertise to provide you with a comprehensive overview of current robotics research. While thoroughly reviewed, some oversights may exist in this synthesis. All references to original research papers are provided in the show notes for those interested in exploring these topics in greater depth. Thank you for joining us for this exploration of recent advances in robotics research. To stay updated on cutting-edge research in robotics and AI, subscribe to our AI Frontiers channel. We publish weekly research syntheses covering the latest developments across the field. Visit our website for full paper references, additional resources, and deep dives into the topics we've covered today. Join our community discussions where researchers and enthusiasts explore emerging trends and debate the implications of new technologies. Follow us on social media for research highlights and updates between episodes. If you have suggestions for future research topics or feedback on today's episode, please contact us through our website. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.